All right, so to finish up the notes here, we're going to look at vapor pressure and changes of the state. So we're going to take a look at what vaporization is, what vapor pressure is, which I kind of explained before, and also sublimation. So vaporization here is pretty just another way to say evaporation. It's when you have molecules that are in the liquid phase going over to the surface to actually form a gas. And again, the word escape is used here, like that little picture that I drew for you guys before with the water molecules that are existing in the liquid phase, so they're escaping up here to come out and become a gaseous molecule instead of a liquid molecule. The process of vaporization is always endothermic, meaning you need to put in energy or heat to actually have it happen. And something like water actually has a lot of energy needed to vaporize 1 gram of it. The latent heat of vaporization, if you remember that constant from last year, it was 540 calories are needed to actually change 1 gram of water over to a gaseous molecule of water. Yeah, this is it right here, the heat of vaporization, or the enthalpy of vaporization, same idea. It's the energy needed to take 1 mole of a liquid and turn that 1 mole of a liquid over into 1 mole of a gas. And this is at a pressure of 1 atmosphere. Vapor pressure, which you saw before, is if you have a liquid or a solid and you were to measure the pressure of all those gas molecules just directly right above it, and you have a system in equilibrium, right? That would be your vapor pressure here. So if you go back to the little diagram that I drew before, you have this right here is a state of dynamic equilibrium, or just plain old equilibrium, where you have a you don't have any net change going on, but your water molecules are able to come up here and turn into gas molecules. And some of these gas molecules do end up coming back into a liquid as it condenses. But even though there is net movement, there isn't an overall change in the vapor pressure of this liquid. And each type of liquid or a type of a solid would have its very own vapor pressure depending on how strong the forces are going to be between these molecules over here, which is what you're going to be writing into the next section. If these forces between the molecules are very, very strong, and intermolecular forces are actually going to be covered on Monday, but we have looked at 3 different kinds of intermolecular forces in the past. And by past, I mean honors chem and gen chem. You looked at something called London forces that exist between molecules. These are the weakest type of intermolecular forces. We also have something called dipole-dipole forces. And these are the types of forces that exist between polar molecules, so it's stronger. And then out of the 3, you have something called hydrogen bonding, which is really a type of dipole-dipole interaction, but of the 3 types of intermolecular forces, hydrogen bonding is very strong because it involves a really big difference in electronegativity between the hydrogen bonding with NO or F with NOF here. So if you're taking a look at something like water H2O, right, has the lone pairs here, and you know that this is a polar molecule. It actually also exhibits hydrogen bonding over here as well, which is very, very strong. So the forces between these molecules, these intermolecular forces, are very, very strong forces. It's actually really, really hard for these molecules to try to escape from the liquid phase and go and turn into a gas because the forces that are holding them together here are very, very strong. So not a lot of molecules are going to be able to come up here. So thus you would have a very, very low vapor pressure for molecules that have very strong intermolecular forces. So let's take a look at that. if there is high intermolecular attraction, and let's give an example of that, like hydrogen bonding here. And remember, this is not a very good name because it sounds like it's a bond, but it's actually really a type of intermolecular force that exists. But if you have some sort of a liquid with a very, very strong intermolecular attraction, then right above it, you're not going to have a lot of these liquid molecules turn and escape into a gaseous molecule. So your vapor pressure would actually be very, very low here. Okay, because again, you have that scenario where you will not get a lot of these water molecules or whatever the liquid is turning into a gas because the attraction between the molecules in the gaseous phase or in the liquid phase are so high. Versus if you have a liquid with very, very weak intermolecular attraction, for example, London forces, and we will go back and review all these forces on Monday again. They're going to have really, really high vapor pressure because if there's not a lot of really strong attraction between these molecules that are holding them together, they're going to want to escape like crazy just because they can, right? So they're going to want to get out from the liquid phase and turn into a gas. So you would end up with a ton of gaseous molecules right above the liquid here. So if you took the pressure of all these molecules, it would be a very high vapor pressure here. An easy example for something like this would be a lot of different alcohols. So alcohols exhibit a little bit of hydrogen bonding, but a lot of the molecule actually does exhibit a little more of your covalent kind of bond. So there's a little bit of London forces, which are weaker than your hydrogen bonds. So these guys are actually able to vaporize quite easily because there's not a lot of force holding them down. And if you ever opened up a bottle of acetone before or nail polish, remember, probably within a few seconds of opening the bottle, you could actually smell the gaseous molecules in the air. And it's because of this. They have very little intermolecular attraction, so thus they're able to evaporate quite well, and thus we would use the word volatile to describe them. And the vapor pressure also would go up with temperature. If you were to heat something, these molecules have a lot more kinetic energy, and thus they're able to escape a lot better because of that extra energy that they have to turn into a gas. And variation. I think you guys already wrote this part down right here. So the very, very last part of the notes here is the definition for sublimation. So we said earlier, this is when something goes directly from a solid out over into a gas. And the reasons for why sublimation could happen, and a pretty easy example of this is dry ice, which you could buy as a solid, and then you'd see it right before your eyes turning into a gas. And solids have some vapor pressure, just not that much, right? Because it's a lot harder for those molecules that exist as a solid to escape as a gas. But especially solids that do not have a lot of intermolecular attraction, like for example, CO2, if you were to draw it out, it looks like this. It's a linear molecule here. And the type of intermolecular force that it would have is London force. So you don't have any permanent dipoles on this linear molecule. So very, very little attraction between CO2 molecules for each other. And thus, these molecules are much more likely to escape from a solid phase over into a gas because there's not a lot of intermolecular attractions that are actually keeping them down. And that is all.